Well, good morning, good evening, good afternoon to everyone. Welcome to the CRM Camp Seminar. Today we have the pleasure to have Florent Bréhard from, Uppsala University and Université de Lille. He just began a new position, a permanent position. Congrats to him at Université de Lille in France. So he's back home. Florent got his PhD in computer science in 2019 from École Normale Supérieure in Lyon and LAAS CNRS in Toulouse, France. He was supervised by Nicolas Brisbard, who's here, Miora Joldes, I think she's also here, and Damien Pousse, where he developed rigorous numerics and symbolic numerical algorithms for function space problems. He's currently finishing, he just finished a postdoc at Uppsala University in the Kappa group under the supervision of Warwick Tucker, who's also, who moved to Australia, but he was in Sweden when Florent began there. And starting from February 1st, as I said, he will join the CNRS in Lille, France, as a permanent researcher. So please, Florent, the floor is all yours, and you can talk to us about Galerkin method using Chebyshev for linear ODEs, please.
Yeah, so thank you to all of you. Thank you to the organizer for inviting me to this very interesting seminar. Well, I'm really enjoyed giving a talk here. So first remark, I just got a cold like a few days ago. So if my voice is not sufficiently clear or something, don't hesitate to interrupt me, of course. Okay, so what I'm gonna to present today is it's not a new computer-assisted proof for some theorem in mathematics, nor a software demonstration, let's say, as accomplished and mature as the one of David. I think it was two weeks ago. It's kind of in between. So what I'm going to present is more an algorithmic and complexity analysis point of view about the validation of ODEs. So you may ask why I'm focusing on linear ODEs in this non-linear analysis seminar. That's a good question. Well, the thing is that from a complexity perspective, let's say an important building block of the validation of general ODEs is the linearized part, the linearized version. I think you all develop different methods for ODE, and for a wide range of those methods, this linearization is an important step. And so from a complexity perspective, it's quite relevant to focus first on this part, and of course then to extend to wider class of ODEs bounding the linear terms. But yeah, I will focus on linear ODEs and to present the complexity analysis of this. Okay, so as an example, throughout this talk, I will use the Airy function. So this is a well-known function by physicists, for example. I think one of the most common definition is this improper integral that is not that easy to manipulate. Well, another way to represent this function is to use the differential equation. So it's called a D-finite equation. It's a linear ODE of order 2 with polynomial coefficients, and you have here those transcendental initial conditions. So here's the plot of the function. Well, as you know, like an ODE of order 2 has a solution space of dimension 2, and the other canonical solution in this solution space is called the Airy function of the second kind, and it's an exponentially divergent function. So that means that if you want to approximate even this very simple linear problem by some iterative method, for example, then at some point you will necessarily follow this like diverging asymptotics. And of course, this is not acceptable for our community where we want to do like rigorous proofs in mathematics using the computer. So I want to briefly give, well, I would say a brief and probably very biased overview of methods for ODE validation in rigorous numerics. So first, I will focus on higher order methods because usually in my work, I prefer not only approximate a function like pointwise, but having a kind of global and smooth approximate of my function I'm working with. And so that's that's what made it possible by those higher order methods. So one of the most well-known tools, I would say, are the Taylor methods. So there are different names for these: Taylor models, Taylor differential algebra. So many names for related methods. Of course, there are subtleties between them. Maybe one of the most cited and well-known implementation was the one in the end of the 90s by Makino and Bréhard. I think the software called Cos Infinity. And there are also a lot of different software that made it possible to use the Taylor methods in different fashion, the flavors. There is in CAPD, there is in Finode LP for maybe one of the most well-known one. Well, David told us about an implementation in Julia also. So, well, there are a lot of implementations. Of course, Taylor methods are not a silver bullet, and there are some examples where you would like, for example, suppose your function has singularities in the complex plane, so the Taylor method will be limited by the singularities, and then you have to subdivide and to provide piecewise approximation of your function. And suppose that for some reason you want to have like a global smooth representation, then you can use other ways to to concretely represent function by approximations, rigorous approximations. And so there was a general framework for this called ultra arithmetics in the 80s. I didn't say the people here, so there are Kauer, Miranka, Epstein, for example. And so for those methods, you can approximate with like wider classes of equation. The difference with Taylor methods maybe is that with Taylor methods, the good thing is that the higher order terms, so the higher order derivatives, are directly related to the ODE. You can unfold your ODE and do like kind of forward recurrence. And this is not directly possible if, for example, you work with the Chebyshev basis, which is one of the most used bases after Taylor, maybe. And so another several works way around to work with different bases, and one of the most well-known tools was to use Picard iterations, which after all is kind of this kind of effective way to do what you do on your math textbooks when you prove the Picard-Lindelöf theorem. That's also based on this Picard iteration after all. And so there's different ways that I can mention. One by my previous PhD advisor, Miraj Oldes, working with Chebyshev series. Another one was Thomas Detkulik also. When for other methods, there are also loaner methods developed by Piotr Zigliński and Daniel Wilczak. Another category that I would like to mention, because it's kind of related to what I'm going to present, is the methods based on so either the resolvent kernel of an equation or the green function, depending on how you state the problem. So there are kind of early works by Kedem about that, also a work by Michael Plum. Then I think maybe another work that maybe is not that well known in this community is a work, so it's more from the computer algebra point of view, so it's by Mark Bezzarova. It's dealing with definite functions, so the framework is more restricted. It's really restricted to linear ODEs with polynomial coefficients. But the thing is that it computes everything with rational numbers, and in the end, you get like very, very quick approximation. I had the occasion to use it, and I must say it was one of the most like efficient, terribly efficient tool for this. Well, of course, it's the class of problem is more restricted, but it's something I would also like to mention. Well, and finally, I come to well, probably the class of method that is maybe the most well-known, at least by the organizers of this seminar. So there are different names for that. Maybe I will call them Newton-Galerkin methods because they are based on Newton-like validation related to spectral methods, where you do this kind of Galerkin projections in the space of coefficient. So one of the early work maybe about that is one by Yamamoto. And then starting from the last decade, let's say, there was a wide, like a long series of very interesting works. So by Jean-Philippe J and Jean Bou, all the organizers of this seminar, and of course, other colleagues. Well, I'm quite enjoying to cite those works because it's also one of the first articles I read when I started my PhD. So it's kind of interesting topic even for me. And also with when I was in PhD with my advisors, Nicola and Miura, we worked on those methods to give a complexity analysis, a kind of a general algorithmic framework for, to investigate those methods. So I will call them Newton-Galerkin methods in the rest of the talk. As opposed to these, I'm gonna to present an algorithm that I will call Newton-Picard. So I don't want really to claim that the ideas inside are completely new. You can find ideas from that. So in the works about like using Picard iterations, for example, the work by Miura and colleagues in 2017. And also interestingly, with the Resolvent kernel of the work in Kemel in 1981. So what I'm going to present is that to use this idea that was already used before to provide a new algorithm with a thorough complexity analysis compared to Newton-Galerkin. And of course, I mean, the goal is to prove that we can do better than Newton-Galerkin. Well, the setting is the following. So we're gonna to use like linear ODEs, so with initial conditions. I will restrict the talk to polynomial coefficients for the ODE, but it's not really a limitation because you can replace this polynomial coefficients by a polynomial plus a rigorous remainder. So it's not really a limitation in this work. I will work in an analytic setting where you approximate the function with Chebyshev series, and so you have this exponential convergence on the coefficients. We will use Banach's fixed point based a posteriori validation for this. And the complexity model I will use to compare methods will be an arithmetic complexity model where for simplicity, you suppose that all the unit operation on numbers, so either floating point or intervals, have a unit cost. Okay, so, well, I guess this a posteriori validation scheme is kind of very well known now in the community. I just want to fix the setting. So you start with your linear problem and you give it to your first algorithm, which is your approximation algorithm. So in our case, we will use spectral method, could be something else. And this algorithm, well, it doesn't compute something rigorous. It just computes an approximation that I call wide tiled. So let's say it's a polynomial written in Chebyshev basis, and you give this approximation to the second algorithm. And the second algorithm is the validation algorithm that does everything rigorously. So here I will present both Newton-Galerkin and Newton-Picard in this talk. And together the result is this pair with a polynomial approximation that we hope it's good and a rigorous error bound for the error. So I will call that a rigorous polynomial approximation. Well, so for the, of course, in terms of what we use in terms of computation, for the first step, we will mainly use like only polynomial approximation in Chebyshev basis and only floating point operations. So no rigorous thing at this step, no rigorous remainder, no intervals. And this comes only with the step 2, where you manipulate these rigorous polynomial approximations with interval computations, and also to use a Newton-like fixed point operator to deduce this bound epsilon. Well, among the, let's say, the numerous good properties of such a way to distinguish both steps, one other advantage is when you want to formalize, I mean, to implement this method in a certified tool, for example, a proof assistant that Konstantin was mentioning last week. So it's becoming more and more important in rigorous numerics to be able to say that not only your method is correct, but also your implementation is correct. Because reviewing someone else's code is something super difficult and consuming and not really efficient. So that's also another, like, let's say, perspective in the coming decade for rigorous numerics. So the logo you can see here is the logo of Coq. This is a proof assistant that I use, but of course there are different options. And the good point with such a validation scheme is that from Coq's point of view, the step 1, so the numerical algorithm, it just a alleged good oracle, but it's a non-trusted algorithm. You don't want to implement this step 1 in the formal proof assistant. Only the second algorithm, the validation part, has to be implemented in the proof assistant. So this way to distinguish the approximation step and the validation step is also quite useful if you want to go toward formal proof implementations. Okay, so I will first give to sum up the ideas between behind the first step, the approximation method using spectral method, not for the pure sake of approximation, but also because it will be useful for the validation part later. So here's the problem. You have a differential equation, let's say of order R, linear, with, let's say, polynomial coefficients of degree at most s, but of course you could generalize this, but just let's fix this here, together with initial condition. And usually in spectral methods, the first step is to restate this differential equation into some easier to use functional equation, namely an integral equation. So a possibility for this here is to say that your unknown function is f is the highest order derivative of y, so y to the r, and then you can express the lower order derivative as a stack of integral here, plus some term here depending on the initial conditions. Well, of course, this stack of integral, you can rewrite it using a single integral with this kind of kernel here in the middle. And so by summing all the terms of your differential equation, you get an integral equation f. So namely f plus some k of f equal to some g, where k of f is this integral operator obtained by summing those contributions. So I will write it as this integral of some ft times k of xt. So it depends on both the integration variable and the external variable x here. And the right-hand side is the right-hand side you had before, minus the terms coming from the initial conditions. So the precise formula are not super useful, just to state that it's super automatic to go from one to the other. And if you try this on the Airy example, for example, you will get some integral equation for the second derivative of Airy function here, of this shape. And you see here that you have a bivariate kernel here of order of degree 2. The right-hand side is also of degree 2 and depends on the initial conditions v0 and v1 and so on. Now, suppose that for some reason you want to provide an integral equation directly on the function itself and not the last derivative. Well, you can still do it, but then you have to rewrite your differential equation in this maybe less traditional backward form, where you first multiply by the polynomial coefficients or any analytic coefficients, and then differentiate your function. Okay, so you have this kind of thing. Maybe here don't pay too much attention on the sign alternation. It's a kind of convention to match the so-called adjoint form of differential operators. We will come back to this later, but it's not really a restriction here. So when you have such a kind of equation, you can directly integrate this equation. And so when you integrate this kind of term, you can cancel some integral sign with the derivatives here of order I, and you get some remaining thing here, minus, I put something depending on the initial conditions. I don't want to give more into details. The important point is to notice that you can also get an integral equation directly on y of the following form. And if you try on the Airy function, you get an integral equation that is kind of similar to the one before. It's slightly different because this time this integral equation acts directly on the function, the Airy function directly. So you get this integral equation for the Airy function. Now let's see, when you have an integral equation, either on the last derivative or on the function y directly, it's not important. Let's see how spectral methods proceed. So you have this equation, and the idea behind spectral method is to write this unknown function y as an infinite vector of coefficients in some given basis. So here I will consider the Chebyshev basis, but it could be whatever other basis, of course. So you have here your function y0, y1, etc., so the vector of coefficient. Now this integral operator acts on y as an infinite dimensional linear operator, so an infinite dimensional matrix. And due to the fact that your operator only involves multiplication and integration in Chebyshev basis here, you have this very specific sparse structure that some authors called almost banded. So this is the shape of this operator with just a number. So the coefficients are located on a finite number of rows and diagonals. And then you have to equate it to the right-hand side. Okay, of course, you're not gonna solve this infinite dimensional system. You need something finite dimensional to work concretely on the computer. And the good thing with this operator here is that it is compact, which means that the coefficients in the matrix that tend to 0 when you get far from the origin. So the natural idea behind spectral methods is just to truncate the system into finite order and to solve the remaining finite dimensional system. And also in that case, since you are almost banded, you can use an algorithm designed by Shihan Olver and Alex Thompson that allows you to solve the system in linear time with respect to the truncation order n. So remember here, this in the complexity, r is the order of the equation, s is the degree. So together, r plus s give you roughly the bandwidth of your operator. And so here is linear with respect to n. Okay, so here's a few examples. If you try the Airy function, I think it's here, it's over minus 15 to 15. So with degree 10, so of course it's not sufficient. You have to go a bit further in order to match the oscillations on the left and the exponentially convergent behavior on the right. And I think here on the plot with n equal 50, you don't see any difference. So here are the Chebyshev coefficients of the Airy function that you can, let's say, approximately obtain with spectral methods. And you have this very typical behavior where you start to have this kind of plateau of coefficients. And then at some point, it starts to decrease. So here you are in a log plot, and you can see that you converge faster than any line. So it's basically because the Airy function is not only analytic, it's even entire. There has no singularity in the complex plane. So that's why you converge faster than any exponential. And so software manipulating non-rigorously Chebyshev series, so maybe one of the most well-known is the Chebyshev software in MATLAB. They have like sophisticated heuristic to truncate this series. And so at some point, if it's below, let's say, double precision, you just do not consider the coefficients below double precision. But well, even with very sophisticated heuristic, you cannot guarantee that at some point, like after degree 100, maybe 120 or something like this, that suddenly the coefficient won't go up again for some reason that was not expected. And so in order to provide certain like rigorous proof, we need also validation algorithms to that. Okay, so that was the first step, the spectral method. Now I can come to the validation. So remember the step 1 that we did, we just here focused on complexity, also numerical stability, the asymptotic convergence of your method. But until now, you don't have a rigorous proof. And the rigorous proof will come now with the a posteriori validation algorithm, where, so in my case, I will use the Banach's fixed point theorem. There are different alternatives, a subtle difference between different flavors of it. Well, with this Banach fixed point theorem, the goal in general is to restate your initial equation as a fixed point equation, so the form T of y equal to y. And then if you prove that your operator is like lambda contracting for some lambda smaller than 1, then you can bound and even enclose the approximation error by computing the distance between your approximation and its image under T. Okay, so in particular, T needs to be a sufficiently constructive operator so that you can compute with T. You can explicitly compute with T. And you also see that the smaller lambda is, the tighter this enclosure is. Okay, so let's try with, let's start, with Newton-Galerkin methods. So you restate your integral equation, so y plus k of y equal to g, as a Newton-like fixed point equation, so of the following form, where you have to approximate as, let's say, A, the inverse of the Jacobian of your operator. So here we're working with a linear ODE, so this equation is affine, and so we just have to approximate the inverse of the linear operator identity plus k. Well, of course, identity plus k is an infinite dimensional operator, and you cannot directly represent the inverse. I mean, the inverse is the solution of a problem. So you have to approximate it in a computable way. So the idea of Newton-Galerkin methods is to say, okay, I need to approximate this infinite dimensional operator. So I will do just as in spectral method, I will truncate this problem into finite dimension. So let's say we choose a number ng, which is not related to the degree of your approximation. It's something different. It's just for the purpose of creating a contracting operator. So you choose this ng, and you approximate the inverse of this finite dimensional operator. So you just have to invert a matrix with floating point operations. It's not a problem. And then you have to bound the norm of this operator. And so what is usually done is to split this bound into two parts. Well, I mean, in the works, in the works of Jean-Philippe and colleagues, when you work with nonlinear equation, you usually have a third term which is related to the nonlinearities. Here, I don't consider them, so I only have two terms. The first one is the approximation error, because your matrix A is only a floating point approximation of the exact inverse matrix. Okay, this is not really a problem. But the second part is more interesting, because it's a truncation error due to the fact that the truncated operator k is not exactly k. There is this remaining tail, and this is what you have to bound. So this tail multiplied on the left by your operator a extended by identity. So let's be a bit more specific about the norm we have to choose. Of course, in the ideal world, we would use the infinite norm, because usually we want to work with the infinite norm. But unfortunately, since we are working in a coefficient space, we have to take some conservative norm that behaves well with respect to the Chebyshev coefficients. So here I will consider what I will call the Che1 norm, which is just the sum of the absolute values of the Chebyshev coefficients, which is like an overestimation of your infinite norm. And so computing the norm of this operator with this Che1 norm just amounts to take, well, the column of the column which has the maximum sum. So for this, we with my previous PhD advisors, I developed like an algorithm to do smart bondings of the columns in order to get sharp bonds. Because remember, if your bonds are not sharp, then you have to use a larger value for this ng that is working with larger and larger matrices. And this is not what you want to do, of course. And I don't want to go into details. The thing is that we prove the following complexity for the validation method based on Newton-Galerkin. So you see here in the complexity, you have two parts in the sum. The first part is related to creating your contracting Newton-like operator. And so your quadratic with respect to this truncation index ng. And the second part is to compute the bond epsilon. So you have basically to apply your operator t on your approximation, and so you get the following complexity. Well, of course, this complexity depends on this number ng that you have to choose to create your operator. And the unlucky thing is that we prove that in the worst case scenario, ng may be exponential with respect to the coefficient, the coefficients of your input equation. So that's the bad thing. Well, if you want to see it, if I go just a bit before here, the thing is that your matrix here, the coefficients, they only decrease in 1 over n in this matrix on the right. And on the left, you multiply by this inverse A or approximate inverse, and the norm of this inverse, so since it's a differential equation, you know, may be exponential in the input coefficients. Just think about the exponential function, for example, you know, y prime is equal to lambda times y, and then the solution is exponential lambda x. So it's exponential in the quantity lambda. So this is why you have this unfortunate exponential bound. So I give you this example for the Airy function. So here I approximate the Airy function over some interval minus a. So here you see the evolution in function of a in the plot. So what we will do just to rescale this minus a over minus 1, 1. And then so you get this, I think it's some a cube as a coefficient in your differential equation when you rescale, and you see that when a grows, then this number ng grows exponentially fast. And I think as soon as a is equal to 10, for example, you need ng equal to 500,000. So imagine working with matrices of size 500,000 with interval computations and so on. So it's becoming rapidly intractable.
Florent?
Yeah?
You have a question in the chat.
Oh, sorry. I don't have access to the chat, I think, unless I...
Well, I can read the question.
Oh.
So it's from Piotr Zliczynski, and he asked if should the complexity depend on the desired error or the length of the domain?
Oh, here in the complexity is, oh yeah, so the length of the domain first, I suppose that I rescale it over minus 1 to 1. So you just, so the problem of the width of the domain is transferred as a problem of the magnitude of the coefficients. Like for the Airy function, if you just rewrite this Airy equation over minus 1, 1, just multiply by a, you get some a to the cube, for example, in one of the coefficients. Okay, so it's basically the same problem. And the other question is the desired precision. And so here the complexity you have, I give the complexity in terms of the degree of the approximation to be validated. Of course, you can relate this n in green here, which is the degree of the approximant. You can relate it to the target precision. You can give rough a priori estimate on how big the nth coefficient of your Airy function will be, for example. Okay. The thing is that here, the only quantity that we want to somehow eliminate in this complexity analysis is this ng, because this ng is not given by the user. It's the truncation index that you will choose to define your contracting operator. So only just keeping like this and not mentioning what ng is kind of cheating. Another important point also is that, for example, for this Airy function, something disappointing is that you can expect that n in green here is not that high, it's not that large, because for the Airy function, it converges quite fast. But typically, when a grows here, the interval, then the number ng grow really faster than this n. N in that situation, to target an error of something like 10 minus 10 or something like this, n would remain small, maybe 100 or 200, something like this in this example. But this ng, it grows really, really faster than this n. And this shows that the validation step costs really, really more than the approximation step. And this is something that we would like to avoid. Okay, let's conclude about Newton-Galerkin methods first before coming to Newton-Picard. So those methods, they were successfully applied to a wide range of equations. So that's really incredible, the number of equations that were targeted with this related methods. So, and here the organizers of the seminar are great specialists about that. So you have nonlinear ODEs, you even have PDEs, delay equations. Or also, for example, you can work in different bases, maybe Fourier bases, to work with periodic solutions of some equations, and so on. And so it was used in many computer-assisted proofs, like celestial mechanics with the n-body problem, also with Navier-Stokes equations, the Rice conjecture in delay equations, and so on. Now, if I want to sum up the limitation that I mentioned before, so first, there is this exponential growing indexed ng that can be a problem if you work with a tricky instance with like over a long interval or with something with high variations. Another thing is that those methods are quite dependent on the basis you are working in, which means that if you want to change from Chebyshev to Fourier or Legendre basis, for example, then you have to redesign all your algorithm to bound differently the columns and so on. So it's a lot of work, it's from the theoretical point of view, it's not that costly, but if you want to implement it or even to formalize it, then it becomes quite heavy to each time you want to change a basis. Another limitation is that you're bound to use a norm that is suitable for this coefficient space. So you cannot directly work with the norm you want to work with, but you have to use some overestimation that is compatible with the coefficient space. And the last point is that from a formal proof point of view, which is also something I'm quite interested in, maybe these methods are not, let's say, you can formalize them, but they probably require a lot of work because you work with this infinite dimensional matrix. So, and you have to do some, like a lot of analysis to bound the coefficients. So it can be a bit tricky. And I think all of those limitations in my point of view, so my interpretation is that with working with this infinite dimensional operators, we somehow forgot about the algebraic structure of the integral operators. And so that's why I'm gonna to present you an alternative method based on Picard iterations, or more precisely on the resolvent kernel. How much time do you have? Okay. First observation. Take this operator identity plus k inverse. And so this operator is the inverse of an almost banded operator. And in general, the inverse is something dense. Well, here what I did is that I just plotted the coefficients with the color meaning for the amplitude of the coefficients. And even if this operator is dense, you see that the coefficients are rapidly decaying far away from the diagonal and some initial rows. So we can say that this operator is somehow asymptotically almost banded. So it's not really almost banded, but you have a special structure that that perhaps we have forgotten before. And the reason behind this is because of the Picard iterations. Well, you can write your identity plus k minus 1. You can formally write it as this Newman series with this iteration of the operator. And well, if k has a certain bandwidth, then k squared will have the double bandwidth, and so on. So each iteration has a larger and larger bandwidth, but you just hope that these iterates, they converge, so that the resulting thing is dense, but if you go far away from let's say bandwidth or twice or three times, then the coefficients decay kind of rapidly. Well, more formally, if you take two integral operators with polynomial kernels k and l, and if you compose them, then the result is again an integral operator, and the polynomial kernel is given by this composition law, which is kind of convolution-like law. So this is the following. Well, to see it, just apply the definition of the composition, just invert the integral signs, and here you can extract this kernel in the middle here. So if you take the iterated kernels k star n, well, you can easily prove that they are bonded by this kind of exponential type bond, and by this I mean some constant m to the n divided by a factorial of n. So of course, m is related to the magnitude of your input equation. So if m is big, then the first iterates, they start to grow and grow and grow. But at some point, the factorial will win. And so you have this decaying behavior. So you can write the sum, the alternated sum of this iterated kernel. And so you can write that this identity plus k minus 1 is equal to some identity plus r. And r is an integral operator with polynomial kernel given by this Gothic r here. And this is called the resolvent kernel. Okay, now we have everything to give the main lines of the Newton-Picard algorithm. So first, compute an approximation of the inverse operator identity plus k by computing an integral operator r tile of polynomial kernel r tile approximating the exact resolvent kernel. So we just want to compute a polynomial approximation of this analytic resolvent kernel. And once you do that, then you can define this Newton-like operator this way, and you see that the definition only involves integral operator with polynomial kernels, so you can explicitly compute with those operators. Well, then you have to bound the linear part of this operator, so it's kind of straightforward. You have this sum of 3 integral operators. Here you have a composition, but it's again an integral operator. So the result, this epsilon part, this remaining part that you have to bound, is an integral operator, and you can explicitly bound even by over approximating the norm if you want, by the Chebyshev norm, for example. And you compute some value lambda. And if R tilde is sufficiently close to R, then this lambda will be smaller than 1. And so you can apply the standard validation procedure by computing the distance between your approximation and its image under T. So it's something completely computable. You bound it and you get your error enclosure. Well, that looks perfect. Well, of course, the question is how to efficiently approximate this operator R, this resolvent kernel R. Well, if you look at the definition from the previous slide, you can go here, here. You can, of course, try to approximate these iterated kernels, like truncate this sum to finite dimension and to approximate. But it will be very, very costly to iterate this operator. So it's not the best thing to do. Instead of this, I propose you the following formulas. Well, those formulas are not completely new. I mean, I just adapted them for this framework, but I mean, it's kind of standard thing related to the green function of a differential equation, you know. So you have your differential equation, you have a corresponding integral operation, integral equation acting on the last derivative of your function. And so the resolvent kernel may be written that way. So you have here a sum of R terms of a product of some function of X and some function of T. So it's not a general bivariate function that could be very difficult to approximate. It's just something that is of a bivariate function of rank R. So it's a good news for us. So let's be more specific about what this function phi I and psi are. Phi I, they are let's say the canonical basis of the solution space of the equation L of phi equal to 0. So it's the homogeneous equation associated to your equation. So since you want the last derivative on those functions, I mean the derivative of order R, then you can directly solve the same integral equation. You just have to select the right-hand side, hi, to match those canonical initial conditions. And if you write this this equation as an equation of order 1, but of dimension R, well, this is a standard way you can see it. Then you get this fundamental matrix phi. So solution of phi prime is equal to ax times phi of x. This ax is a companion matrix associated to your differential equation. And so this function phi I, they are just like the first row of this fundamental matrix.
Florent?
Now, how to get the psi I? What are the psi I?
Florent?
Yeah?
There is a question in the chat. Perhaps, Jonathan, you can ask directly.
Yeah, so how did we get k again? I believe it's an integral operator, but do we know that it has norm bounded above by 1?
Sorry, the operator k, here. Is operator k is when you transform your initial differential equation into an integral equation.
Mm-hmm. So does it have norm bounded above by 1? Because we're taking a Neumann series for the inverse.
Yeah, no, it's the norm is not bounded by 1. This is why taking the Neumann series here, I just said you can formally write it, but then you have to prove. So in fact, the norm of k is not smaller than 1. The thing is that the iterates at some point they will converge. But you cannot directly see it by saying that k is smaller than 1, so the iterates, they converge. It's a bit more tricky. You have to use this proof that I briefly mentioned here. With the iterated kernels, you have this kind of bound of the form m to the n divided by n factorial. So for the first few n, the bound may be huge. I mean, maybe something very big. But at some point, the factorial will win over over this m to the n, and you will get something converging. So no, this operator k may be something of, a norm like way larger than 1. I mean, there is no possibility to ensure that k, of course, if you just take a very, very small segment, you can always ensure that k is smaller than 1, and then you can subdivide. But typically, this is not what you want to do here. You want to have a global method here over the global segment. So the answer is no, k is not smaller than 1. But some interrate will at some point will be smaller than 1.
Thank you.
Okay. Okay, so to get the function psi, they are related somehow to the inverse time operator, this inverse time fundamental matrix. So you take this fundamental matrix phi of x, you take the inverse, just take the transpose, and you get a matrix psi that's like satisfy this adjoint differential system, like the following, and we want to extract the last row of this, and this is give you the function psi. And another way to see that is to say that the function psi I, they are the solution of the so-called adjoint differential equation to psi. I will show the adjoint equation just after. And so you just have to solve the adjoint integral equation, again with spectral methods, to compute this function psi. Okay, here's the adjoint equation of this L. So this is, now you understand why at the beginning I chose this sign alternation for this backward form, is to match this adjoint form of differential operators. So you just commute the symbol x and the symbol derivative and put a sign minus each time you reverse them. And so you get something of the following form. And if you started with the L star instead of L, that is, if you had a backward differential equation to validate, then the resolvent kernel, this R star, is really the same. You just have a sign minus and you just commute the role of t and x. So it really works symmetrically in both directions. And the thing to remember is that to approximate those functions phi I and psi I is just, again, spectral method to apply to the integral equation and the adjoint integral equation. So it's really more efficient than just approximating the iterated kernels. Okay, now let's conclude briefly with the complexity of this way to do this new algorithm. So the first step is to approximate this resolvent kernel by using spectral methods to approximate the phi I and psi I, let's say of some degree nr that you choose. Well, this is the complexity, using again this Olver and Townsend algorithm for almost bounded metrics to work with spectral methods in Chebyshev basis. Then you have to bound the norm of the linear part, and I think the most costly method here is to perform the composition of the two kernels here that you have here. So this is why you have something like nr to the square. So here is somehow the bottleneck of the method. I just assume, of course, we could use like fast multiplication of polynomials. I just don't want to give the complexity in that scenario, because fast multiplication of polynomials with interval coefficients is still something, let's say, a bit debated, not completely mature. So just to keep it simple, I prefer keeping this quadratic complexity. And last, you have to compute this defect. So this t of y minus y. And so here's the complexity, again, assuming the naive quadratic multiplication algorithm. Now, if you want to compare, so, well, you see that the total complexity is somehow similar to Newton-Galerkin. I mean, you have this nr to the nr square, where you have this ng square in the Newton-Galerkin. Now, of course, the crucial question is, how does this ng compare to this nr? And remember, in the kind of ng, we have something that was, let's say, linearly bound by the inverse operator, which was itself exponential in the input equation. And here, since nr is just using polynomials to approximate analytic function for the resolvent kernel, we have this exponential decay, which means that nr just has to be logarithmic with respect to those functions phi I and psi r, which are themselves related to the inverse operator. So those functions, they are exponential in input coefficients. So in total, you get that this NR is only polynomial in the input coefficients. So if you want to just see that in practice for this Airy function, this gives you, for the same example, the values in orange for this NR. And so you see that it evolves like not too fast. It means that in those examples, like a degree 100 is sufficient, where for Newton-Galerkin, you have to manipulate matrices of size 500,000. Okay, how much time do I still have? Well, just 2 minutes to conclude. So for this, just to brief the main ideas of this new algorithm is that instead of using truncation in coefficient space, we directly manipulate the integral kernels of the associated integral equation. We get a polynomial time complexity rather than an exponential one. Other advantages, I think, that we still need to investigate is that this method is more flexible with respect to approximation, bases, and norms. Because in all what I described, computed this approximation of the and so on, I mean, just like checking that the resulting integral operator is small is something that is quite basis and norm independent. It's not super specific. And well, to do those examples that in particular I show you for this Airy function, I implemented this in C. Well, of course, there is a lot of future work to continue along those methods to do like really more interesting problems than only linear problems. So like to include, for example, the ready polynomial approach to get the nonlinear ODE. And I think it's quite doable because, after all, you just here we just did like the linearization part, and this nonlinear bonding part is kind of, you can interface them with different way to bond the linear part. Other interesting extension would be to work with like a singular case. What happens if you have a singularity on your domain of approximation? So which kind of basis you can use to represent those singularities, or maybe to work on unbounded intervals with Hermite polynomials, for example, and so on. And finally, also something that I probably will do like in like the coming months maybe, is to provide like a certified implementation in the Coq proof assistant, because the goal is also to have like a certified calculator for differential equations. Well, I think I already talked a lot, so thank you to everybody, and please don't hesitate for questions.
Great talk. Thank you very much, Florent. Are there any questions or comments?
Well, if I may.
You may.
Okay, thank you. So the computation of this Gothic R operator, so I had the impression, but I want to be sure if I'm correct with that. Isn't that just to approximate the Green's function in an appropriate way? You see, the Green's function has precisely that structure. This R is the Green's function.
Yeah, it's really related to the Green function. It's not exactly the Green function, because technically the Green function is for the integral, for the differential equation, not the integral operator. But they are really similar in some way.
And that means you have what you do actually when you compute this error between R and R tilde is you calculate the error of the Green's function.
Yeah. Well, the thing is that instead of using some theorem to bound the error with some properties, we just like check here that the remainder here, so this linear part, is something small. Of course, when you want to give a priori estimates for how big an R has to be, then here you can use some theorems to do some a priori estimate. But if you want just to validate, like to implement this in Coq, for example, you just have to check that the resulting residual integral operator here that I call E is small.
Of course, yeah, sure. Yes. Okay, but it's essentially based on Green's function estimates. That's what I wanted to.
Yeah. It's mainly based. Yeah, it's, well, let's say closely related.
Yeah.
Really closely related.
Okay, thank you.
So Florent, there is a question in the chat. So from Hiroshi Murakami from Tokyo Metropolitan University, is asking, what if we use piecewise basis instead of basis in wide range?
Yeah, I would say a good thing with this is that it seems quite possible to use piecewise basis in that case, contrary to, well, Newton-Galerkin would be that slightly more difficult because if you want to work with coefficient space, like piecewise coefficient space, that could be a bit more tricky. But here, as long as you have an approximation, so here the slide is the correct one here. As long as you have an approximation of this R, so as long as you have this R tiled, you can actually work with any type of approximation for this R tile. Here I work with Chebyshev, but that could be piecewise Chebyshev. And of course, that's something that should be implemented because, well, except if you want to go for very, very high precision, sometimes it's really more convenient to just subdivide your domain, as long as you're okay with doing that, of course. As I mean, here you just need to, you typically just need to have multiplication, addition, like standard operation in piecewise basis, just to be able to perform this step 2 here, step 2 and step 3. But that's all. And you can really work with like splines or something like that. And in theory, there is nothing against that. Here I restricted, in that talk, I restricted to Chebyshev basis in order to give like a clear complexity estimate on this degree that you need and so on, which would be more tricky for splines and probably less efficient asymptotically. But in practice, yeah, maybe working with splines, for example, could be something interesting to do.
All right. Other questions or comments?
Okay, I think I can see the chat now. Okay.
Okay, I have one. Oh, well, I have one. Yeah. So you mentioned, Florent, that the proof, I mean, the verification in Coq could be, or in your vision, like is a little bit tricky with the Newton-Galerkin approach because of this infinite dimensional matrix and stuff. Could you be a bit more elaborate? Because of course we are developing this Newton-Galerkin for a while, and we were thinking of eventually doing a Coq verification, but I want to know what, because I don't know how to use it. So let's say you have more experience than me. So what's exactly the, I mean, is it fundamental, the fact that it's an infinite dimensional matrix? After all, it's a finite block and a tail. So if you have a class of problems, say initial value problems in ODEs, for which you know always what's going to be the structure of that matrix or that operator, then can't you handle that with Coq?
Yeah, of course, it's totally doable. There are, I would say, two main obstacles. Maybe the first one is like working with this infinite dimensional matrix. You have to somehow to formalize all this like projected operators, so these projections and so on. You have to formalize this Banach algebra setting.
Yeah.
So, and I would say the current state of art in Coq is that, well, you have to do a bit of work, which could be very useful for some people coming after you. So, I mean, it's not something useless, but it requires, I would say, probably more work to formalize this. And the other point is that, so I don't know exactly, I still haven't had the occasion to look into your code, but in the paper I wrote with Nicolas and Miura, so we provide some like a bit refined bonding techniques for the tail by some tricks. We use some tricks in order to make this ng as small as possible. And if you want to implement this kind of inequalities in Coq, by say, okay, I just have to shift the coefficient and do this kind of trick and put some part here, that could be a bit tricky to implement. I mean, even if when you read or write the article in math, it's just already a bit like not super, you're not like super enthusiastic to read this kind of stuff. So like formalizing it is like, oh, it's a bit of work. And also it's a work that is really dependent on the basis in which you work. That is, if you want to work in Fourier instead of Chebyshev, well, maybe Fourier is a bit too close, but maybe Legendre, then you have to redo all this technical work again in Coq, and that would be something, well, a bit time consuming, but it's not undoable at all.
Yeah, I mean, I was just thinking, initial value problems in Chebyshev, say, for this class of problems, and then that's, but okay, yeah, I get your point. I have more questions, but I think Michael had one, so.
All right, thank you. It's also my second already, but anyway. So when you move from initial value problems, say, to ODE boundary value problems, then your operator K is no longer of this Volterra type, but it's of Fredholm type, and also the kernel is much less well accessible.
Yeah,
So how much of what you said can be transformed to this boundary value problem case?
Yeah, that's a very good and tricky question. That will be indeed really more tricky. Maybe the best thing to do is just to well, I think well, I already tried to look if it's easy to find the green function to approximate it. So maybe there are like works I'm not aware of that give kind of simple formulas to do this. Otherwise, it's probably something like you also include like your initial conditions as like part of your unknown variables, and to do this kind of to integrate this unknown initial condition into the unknown thing, and to design your operator together. Yeah, that would be like the rescue solution. Of course, it would be better if you have, for example, nice formulas for this.
So that's the point. If you can still do this complexity analysis, right? So what we usually do with boundary value problems, we don't use the Green's function, but we use as you may know, we use this sum bounds for the inverse operator, as many people do when treating boundary value problems, and but not going into details of that operator with respect to explicit formulas. And maybe that's what you can do with initial value problems. But my impression is that you get in trouble when you go to boundary value problems, even for ODEs. Even worse, of course, if you go for boundary value problems for PDEs.
Yeah, exactly. That will be something more difficult. So I think that going to ODEs with initial value conditions is something that, as I mentioned, is just like including this nonlinear term, something really doable. Going to the boundary value problem requires like, adding some new ideas or trying a way to approximate cleverly the green function, or there is something to be done. I don't have the answer yet.
All right, thank you.
Other questions?
May I ask a question?
Sure, Piotr.
Yeah, can you show this complexity estimate when you have this polynomial? And
this one?
No. When you said something is polynomial, something is exponential.
Oh, yeah.
Oh, okay. So AI is what? On the right hand side, I mean, AI.
AI, they are the input, they are the coefficients of your differential equation.
Okay. Those are coefficients. Okay. Okay. But then, and those phi's under this capital O, what were those?
So the phi and psi, they are this function related to the resolvent kernel.
Okay. So in a sense, so they are also coming from differential equation. Okay.
Yeah, they are somehow like the solutions of the homogeneous system.
Okay. So can you go back again to that? Okay. And then, so in this capital O stands that it's exponential or something. I mean, because how do you see from what you wrote that this is exponential and the other thing is polynomial because of this log, right? I mean,
yeah, because the phi and the psi, since they are solutions of the differential equation, they might be exponential with respect to the input equation. So it's like considering y prime is equal to lambda times y, and the solution is exponential lambda x.
Okay. And then if I will rescale equation, then this factor will also pop up, right, in those estimates. Okay.
Yeah.
Okay, thanks.
But does that mean that if you were to compute, I don't know, bounded orbits, I mean, let's say periodic orbits or connecting orbits, or you would not have this exponential, you would not have that, right? It kind of, I mean, for linear ODEs, I understand that you will have exponentials naturally, but say if you're after bounded solutions of a nonlinear ODE, and you're after specific type of objects, say, bounded orbits. So then this does not necessarily apply, does it?
No, I mean, it depends what kind of equation you use. I mean, here in the Airy function, for example, it seems that you're not exponentially diverging, but the thing is that in the solution space, there is another diverging solution. But if instead you're working with maybe like the ODE for sine and cos, then the bonds are not that pessimistic.
Right.
It's still, usually the NG is still larger than NR because you do this kind of over approximations and so on, but you don't have this exponential behavior. So if you work with like periodic solution, as long as all the solution in your solution space are bounded, or I mean periodic or something like this, then it's, I guess you don't have this exponential bond.
Mm-hmm. Okay, yeah, thank you. There's a question in the chat. Can we use the Chebyshev best approximation for 1 divided by 1 plus k instead of Neumann expansion?
Where is the question? Because can we use the Chebyshev best approximation for... To approximate, yeah, this operator. So I don't really use, I mean, the Neumann expansion was to explain where it comes from, but in practice, I use spectral methods. So spectral methods is not the best approximation in the sense of Chebyshev, but it's a near best approximation. Of course, if you want to use like, I'm not exactly sure that's the question, but if you want to use the best approximation, the best polynomial approximation of degree n to the analytic resolvent kernel, then it's a question of finding like the minimax approximation. And that's an optimization problem. So maybe you would just decrease a bit the degree for the same error, but instead of having just a simple linear system to solve, you have a semi-infinite optimization problem to solve. So I'm not sure that in terms of complexity, you would win with this strategy. But well, maybe that's possible.
May I ask again?
Of course.
But even on that picture here, which is displayed, so what was the criterion for choice of those n's? I mean, I can always take bigger n. So you had some criteria that something is smaller, I don't know.
Sorry, I'm not sure to understand.
No, you have this graph, and you have a graph of NG. Yeah. And R depending on the size, but you somehow decide that you take this n and in other case the other n. What was the criterion for that?
Oh, the criterion in this graph is to show somehow the minimal NG and NR in order to get a contracting operator. Let's say to get a lambda smaller than 1/2, maybe, you know, something like that.
Okay, so if my question is that at the end I would like to have like error less than, say, some epsilon, so this NG will be at least that thing. Eventually we will need to increase it, right?
Yeah, because this is the value of NG that you have to choose, for example, in the Newton-Galerkin, in order that your truncated operator is sufficiently close so that you get a lambda smaller than, let's say, 1/2, and same for this NR.
But then if I will ask that my result should be less than epsilon, so it will be kind of linear in this NG, which is here. I mean, once I have contraction, I may need to still use some bigger NG. Okay, so how this will depend on this epsilon? Can you kind of?
I mean, here the epsilon that you mean is well, just to be sure that we talk about the same thing, is not the epsilon of the final approximation, like it's not the accuracy on your final approximation. It's just the contracting ratio of your operator. Well, of course, you may want to have an operator as contracting as an epsilon if you want very, very, very tight bonds in the end. The comparison will still be the same for between both. It's just like rescaling. So I mean, here the complexity is somehow simplified. You probably have like a log of epsilon minus 1 or something like this in the complexity as a factor between both.
In this capital O, I will have factor log over 1 over epsilon.
I mean, the thing is that you want lambda being smaller than epsilon, and then you give a bound for this lambda, So in case of Newton-Galerkin, this bond is like the size of the inverse operator. So roughly it's something exponential on the AI divided by this n, because the matrix only decreases in 1/n. So you have this exponential of input coefficient divided by n smaller than epsilon. So then you just put this, then it means that n is greater than epsilon times this exponential or something like this. You see what I mean?
Log of epsilon or something like this.
Oh, yeah,
log
of epsilon.
Yeah,
Log of epsilon.
Over,
yeah,
okay.
I mean, somehow the n and the ng are kind of unrelated, right? You could have a solution that decreases super fast, but then it takes ng very large for a contraction to. I mean, the ng depends on your contracting operator. I mean, you could have a lot of regularity coming from the operator, or not, but the solution itself could be very smooth, right? So n and ng are somehow not so related.
And that's exactly the thing, is that for Newton-Galerkin, this n and ng, they are not really related. I mean, ng can be way larger than n. And for Newton-Picard, really the motivation of this work was that this nr is somehow the same as n, roughly speaking. I mean, for nr, you have to consider all the solutions in your solution space. So maybe one is better than the other, so you can have some difference between them. But roughly speaking, this nr is related to the approximation of the worst solution in the homogeneous equation, whereas this ng could be really way larger and unrelated to the solution space. Well, not really unrelated, but really more pessimistic. So really the motivation behind this work is that the validation should be not really much more expensive than the approximation itself.
Yeah, I know we face this all the time. I mean, it's for us, it's the Z1 bound, and I mean, it's basically the same as your problem.
Yeah, I think you call it Z0 and Z1. Yeah, Z0, I think.
Yeah, and we need to pad a lot, and then we need to pad, and sometimes we need to put, I don't know, hundreds of zeros after the numerical solution reaches 10 to the minus 16, and it's really annoying. So that brings me to my question that, you mentioned that Coq could be having difficulties with your kind of ad hoc or your kind of approach to kind of minimize the ng. So can you be a little bit more explicit about how do you try? You said you work with Miyohara and Nicolas about trying to minimize this ng. It was a little bit, it would be difficult to formalize it, but mathematically, can you explain the ideas? Quickly or not? Is there like
It's nothing super deep. It's just finding formula. So let me remember. If you want to bond this, and well, you have an infinite number of columns to bond at once somehow. And the thing is that if you use crude bonds for it, just by saying, okay, this question is like divided by n, blah, 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 and you get crude bonds, then you get some bigger value. And well, I think the way we did it just to compare the first neglected column to the others and do a kind of second order, like not to bond directly like the nth column, but to bond the difference between the nth columns and the ng, here's called the first neglected column, and to do this kind of thing to, well, to get a bit sharper bonds. So in practice, we gain you can gain a factor like maybe sometimes 2, 3, 10 for this truncation index. Sometimes you can really gain something. Of course, it depends how you bond. I mean, we really compared it to the naive way to bond. I don't know exactly in your code, Jean-Philippe, how you bond exactly the columns. There's a lot of ways to do that. So, well, the intuition is that in practice, we observe that usually the first neglected column here, so the ng plus 1 here in the plot, it tends to be like the column of the biggest magnitude, the highest magnitude. So it should be, this column should give the total norm of an operator, but it's kind of impossible to prove. It just like in most cases it's happened, but so of course you have to bond all the columns to find a way to bond all the columns and as sharp as possible.
Okay. And this trick is in which paper?
Well, I call it trick. It's just, I don't want to make it something like, well, it's
I know, but let's say for me, anything with, it's a paper with Nicolas and Miyohara?
Yeah, I think I only have one paper with both of them at the same
Okay,
time.
so that's
Yeah,
this
this
one.
is this.
Okay, all right.
ACM, transaction of mathematical software.
Okay. Are there any more questions or comments? Okay, it's already 11:20, so there were 25 minutes of questions. I don't think we should be shy of stopping right now. Okay, so Maxime Breden actually is making a comment, not to me. Okay, he said that he's in the Alps, so he's not asking a question, but otherwise he would. But anyway, so let's stop here. Thank you very much, Florent. I think
Thank you
not
for
the
the
only one who
invitation.
enjoyed this talk. It was pretty good. So thanks everyone for sticking around. 20 past the hour. So yeah, so thank you very much, Florent, once again, and we'll see you next week. And Jay will be our speaker next week.
Thank you very much.
Okay, so bye everyone.
Thank you, Florent. It was really great. Thanks.
Thank you.